First of all, I would like to thank the organizers of this wonderful workshop for opportunity to give this talk, and really for the previous workshop of this series, since our cooperation with Peter Cameron was mostly possible after the last workshop of this series. Many thanks. So my talk is on recognition of finite group by its Gruenberg-Kegel graph. This talk is mostly based on the joint results with Peter Cameron. Peter has mentioned our joint manuscript, which is now available on arXiv. First of all, let us give some agreements and definitions. During all my talk, any group is finite. And during all my talk, any graph is an undirected graph without loops and multiple edges. And clique with n vertices is a graph with n vertices, and there is an edge between any pair of vertices. And co-clique is a graph with n vertices, and co-clique is a graph with n vertices and no edges. So it's just small agreements. My terminology is mostly standard for finite group theory. However, I will remind some standard definitions just for best understanding of the main results. First of all, there is a common construction of so-called prime graphs on the sets of integers. Take some finite set of integers, and by prime spectrum of this set, we define the set of all prime divisors of the elements of our set of integers. For example, if we take the set of integers omega 2, 15, 21, and 35, then its prime spectrum is 2, 3, 5, and 7. And the prime graph in this set is the graph whose vertices are elements of prime spectrum of this set, and two vertices are adjacent if and only if their product divides some element from our basic set omega. It's easy to understand that in our case, we can think about omega to be closed undertaking divisors. And as an example for this set omega, the prime graph is the following: 2 cliques, 1 clique containing the only vertex 2, and clique containing vertices 3, 5, and 7. And let us apply this construction to finite groups. Let G be a finite group. The spectrum of G is the set of all element orders of G. Of course, if group is a finite group, then each element order of this group is finite, and the prime spectrum of this group is the set of all prime elements from the spectrum, and or equivalently, the set of all prime divisors of the order of this group. And let us define the Gruenberg-Kegel graph, or GK graph for brevity, or the prime graph of this group. This graph has the prime spectrum of G as the vertex set, and two elements below are adjacent if and only if their product belongs to the spectrum of G. And it's easy to understand that the prime graph of a group is just a prime graph defined with its spectrum. And using very simple group theoretical reasonings, it's easy to understand that two primes P and Q in the Gruenberg-Kegel graph are adjacent if and only if this group contains two elements of these orders P and Q which commute. So it's a rather interesting construction, and Peter has introduced that there are many applications of Gruenberg-Kegel graph to understand the structure of other graphs defined on groups. And in my talk, I will concentrate in the question of characterization of a finite group by some its arithmetical parameters like spectrum, Gruenberg-Kegel graph, or just isomorphism type of this Gruenberg-Kegel graph. Okay, imagine that now let us travel to a magic galaxy. Then there is a magic star and the magic planet around the star and the magic city in this planet. And assume that citizens of this city are finite groups, and their addresses are described by some graphs. And the government of this city wants to create an address book for finite groups. Then let group is a person. The spectrum of this group is the room number in the flat where this group lives. The Gruenberg-Kegel graph is the number, so-called number, of a flat this group lives. The isomorphism type of this graph and prime spectrum together is the number of floor in the house where this group lives. And the isomorphism type is the number of house where this group lives. So our dream is to understand by address what is a person, what is this person. It's easy to understand that if you have a person with passport, and in passport there are signatures, the number of house, the number of floor, the number of flat, and the number of room, and assume that you just know the address. Do you able to recognize this person? Really, first of all, let us understand that the problem to understand what is this person is not trivial. And let us construct a series of examples. First of all, look to the first example. These are two persons sharing a room. Symmetry group on 5 elements and symmetry group on 6 elements has same spectrum, but they are not isomorphic. So they live in the same room but distinct. There are two persons, at least two persons, living in the same flat but in distinct rooms. For example, if we consider alternating group on 5 points and alternating group on 6 points, then the Gruenberg-Kegel graphs coincide, but their spectra are distinct. Moreover, the group alternating group on 5 points is the only group living in her own room, but this group sharing her room with infinitely many neighbors. So it's a very interesting situation. Then the same flat, 2 rooms. In one room there is the only person, and in another room there are infinitely many persons living. And the third example is 2 persons living in distinct flats but sharing a floor. Consider 2 groups, alternating groups on 10 points and the orthomorphism group of fine simple sporadic second Yanka group. You can see that their Gruenberg-Kegel graphs have the same isomorphism type. This type is so-called PO, and in Novosibirsk, my colleagues like to name this graph balalaika. But you can see that these graphs are isomorphic as abstract graphs, but are not equal as labeled graphs. However, the prime spectra of these groups coincide, but the Gruenberg-Kegel graphs are distinct. And one more example. Consider, for example, 5 pairwise distinct primes and their product. Let n be the product of some 5 pairwise distinct primes, and consider the cyclic group of this order. Its prime spectrum is, of course, these 5 pairwise distinct primes, and since this group is abelian, since the properties of Gruenberg-Kegel graphs, each 2 vertices are adjacent, then this group is a 5-clique. So you can take any 5 primes and you will have the graph of this shape. So you can see here persons living in distinct floors but sharing a house. Moreover, there are some houses which are really empty. There are no groups living in this house. For example, our result with Dusan Pragon from Slovenia 5 years ago, there are no find groups whose Gruenberg-Kegel graphs are isomorphic to complete bipartite graph with parts of size 3 and 3. And there are several more known examples of graphs which are not realizable as Gruenberg-Kegel graphs of find groups, and it's another direction on investigation. I will not mention these results, but they exist. And another result more than 7 years ago, result by Sasha Gavrilyuk, Igor Khramtsov, who was PhD student in past of my supervisor, and my supervisor in past Anatoly Kondratyev. If G is a graph, if gamma is a graph with at most 5 vertices, then gamma is isomorphic to the Gruenberg-Kegel graph of a find group if and only if gamma is not a 5-ka clique. So almost all small houses are non-empty. Thus, we have rather interesting map of the city address book, and let us try to understand some rules to work with this address book, to work with find groups via arithmetical characterizations by spectrum, by Gruenberg-Kegel graphs, and so on. Let us define a find group G to be recognizable by spectrum or by Gruenberg-Kegel graph if it's uniquely determined by its spectrum. So any or uniquely determined by its Gruenberg-Kegel graph, respectively. It means that for each find group G, if spectra of G and H coincide, then these groups forced to be isomorphic. If their graphs coincide, respectively, then these groups forced to be isomorphic. Let us tell that group is K-recognizable by spectrum or respectively by Gruenberg-Kegel graph if there are exactly K pairwise not isomorphic find group with this spectrum or respectively with this Gruenberg-Kegel graph. Almost recognizable if it's K recognizable by spectrum or by Gruenberg-Kegel graph for some non-negative integer number K, or unrecognizable if there are infinitely many find groups with same spectrum as G, or in respectively by Gruenberg-Kegel graph there are infinitely many find groups with the same Gruenberg-Kegel graph as the Gruenberg-Kegel graph of G. A very remarkable result was obtained by Viktor Mazurov and Wu Zhishi around 9 years ago. If G is a find group, then the following statements are equivalent. There are infinitely many groups H such that they are so-called cospectral to G. It means that they have the same spectrum as the group G. And the second one statement is there is a find group H with a non-trivial normal solvable subgroup with the same spectrum as G. This theorem is a criteria of unrecognizability of a group by spectrum. And a corollary of this theorem is that only groups with trivial solvable radical can be recognizable by spectrum. This direction is well known and deep, and there are many deep results in this direction. And let me first of all mention about some important part of find group theory, and then I will continue about recognition by spectrum. Recall that a find group is simple if it doesn't contain non-trivial proper normal subgroups. In particular, it doesn't contain non-trivial solvable normal subgroups. And it's our case to consider. A group G is almost simple if it's between a finite non-abelian simple group and its orthomorphism group, as follows. And in this case, we tell this simple group, for almost simple group G, we will tell this simple group S its socle. Find simple groups were classified. It's a very remarkable result in find group theory, finished in 1980, and with respect to this classification, all non-abelian fine simple groups are contained in the following series. Alternating groups. It's well-known series for specialists in combinatorics. 6 series of classical groups. They have double representations, like linear groups, like groups of matrices, or like groups of Lie type of unbounded ranks, or 10 series of exceptional groups of Lie type. These are groups of Lie type of bounded ranks, or 26 sporadic groups, well-known sporadic groups. So let us continue about recognition by spectrum. There is a very big theorem by many authors and still in progress. If L is one of the following non-abelian simple groups, then it's almost recognizable by spectrum. Sporadic group, except of Yanka II, alternating group of degree not equal to 6 or 10, exceptional group of Lie type other than this group, or a classical group of rather large dimension. So almost all non-abelian simple groups are almost recognizable by spectrum. It's a brief formulation of this theorem. And there are some other results. For example, many symmetry groups are recognizable by spectrum. This result belongs to many authors, and the final step was made in the paper by Gashkov and Grishkov 5 years ago. And there are examples of groups with non-simple circle, which are recognizable by spectrum. For example, the direct product of Suzuki group over the field of 128 elements, its direct product of 2 copies of this group is recognizable by spectrum. And our rather fresh result, this paper now accepted to a journal, the direct product of 2 copies of fine simple sporadic Yanka the fourth group is recognizable by spectrum. And this result is a very fresh result by Ilya Gashkov. There is an infinite series of examples of fine groups which are direct product of 3 copies of the same group and recognizable by spectrum. This is archive preprint in archive. So this direction is very active. I investigating, but we will try to think about recognition by Gruenberg-Kegel graph.
Natalia, I'm sorry. May I ask you just a simple question? On the previous slide, there is the theorem, and well, what does it mean? Many authors and still in progress. How many? Who are the authors?
Many authors. Let me remind by memory. Виктор Мазуров, Уджи Ши, Андрей Васильев, Мария Гречкосеева, Алексей Старолетов, Илья Гашков, Мария Звездина, some Iranian mathematicians like Khosravi, some Chinese mathematicians like Chen, and really, I think that around more than 30 papers in this direction.
Oh, I see. You mean that this theorem gives results from different papers?
From different papers, from different authors, and it's still in progress in sense that there is an investigation by, as I know, Alexei Staroletov. They try to find the minimal possible ranks, then these groups are still recognizable by spectrum, or separately, Maria Grechkoseyeva and others try to rule out groups of small, classical groups of small dimensions, like PSL for Q or PSU for Q. It's very fresh results, but really many results. And unfortunately,
I see. Okay, thank you very much.
And let us return to recognition by Gruenberg-Kegel graphs. We have tried to generalize the results by Mazurov and Shi, and have obtained a criteria of recognition of fine group by its Gruenberg-Kegel graph. And the criteria is is really very similar. The following statements are equivalent for a finite group. There exist infinitely many groups H such that they have the same Gruenberg-Kegel graph F as the group G, and there is a finite group H with non-trivial solvable radical with the same Gruenberg-Kegel graph F as G. And it's easy to understand if we have a statement, if the statement 2 holds, then if we take H to be a finite group with non-trivial solvable radical with the same Gruenberg-Kegel graph, then any group which is cospectral to H will have the same Gruenberg-Kegel graph as this group, and then this graph will be the same as the Gruenberg-Kegel graph of G. So the implication from 2 to 1 holds directly from Mazurov-Schiss theorem. And let us prove the inverse implication. Let G be a group such that there exist infinitely many groups H with the same Gruenberg-Kegel graphs as the Gruenberg-Kegel graph of G. And assume that for each such a group H, its solvable radical is trivial. Then the number 2 is non-adjacent to at least one odd vertex in the Gruenberg-Kegel graph of G. Otherwise, the Gruenberg-Kegel graph of G coincides with Gruenberg-Kegel graph of this direct product C2 times G, which is contradiction. And then let us apply a result by Andrei Vasilyev. If G is a non-solvable group such that 2 is non-adjacent to at least one odd prime in the Gruenberg-Kegel graph of G, then the factor group of G by its solvable radical, which we have assumed to be trivial, is almost simple. And then we apply this proposition. We will conclude that these simple circles of almost simple groups, the same Gruenberg-Kegel graphs as G, are such as their prime spectra are contained in the prime spectra of G, which is finite. And the following proposition gives a contradiction. If P is a finite set of primes, then the number of non-abelian simple groups S with prime spectrum of S is contained in this finite set of primes is finite, and is bounded, has an upper bound as a polynomial of degree at most 3. Let us prove this proposition. First of all, we need to apply the classification of finite simple groups, and with respect to this classification, we will consider cases. For sporadic groups, there are at most 26 sporadic groups with this property, really usually less number of groups, but okay, at most 26. For alternating group, we apply the prime number theorem. We mentioned that for alternating group, its prime spectral consists of numbers 2, 3, 5, and so on, up to some biggest number in the prime spectrum. And we can bound it in terms of pi by pi log pi. So it's okay. And for classical groups, we need to prove some other propositions. First of all, let us mention that there is a Gimondi theorem. If Q and N be natural numbers such that Q is greater or equal to 2, then there exists a prime dividing Qn minus 1 and doesn't divide in Qi minus 1 for each I which is less than N minus 1. Less or equal than N minus 1, except of the following 3 cases. So no many exceptions. And using this Gimondi theorem, we can prove the following number theoretical lemma. If P is a finite set of primes, and if we take a group of Lie type of rank N over the field of order Q, which P power L, then the number of possibilities if the prime spectrum of S is contained in this finite set P of primes, then the number of choices for P is at most the order of this set pi, it's clear. There are at most the order of pi plus 1 choices for this number L. It's a direct corollary of Zygmundi's theorem, since for each group of Lie type, the number q minus 1 divides the order of this group, and then we apply the Zygmundi's theorem and understand there are at most the order of pi plus 1 choices for L. And if we take the number of pi as distinct divisors of L, then this number is bounded by the order of pi plus 1. It's similar, a corollary of the Zygmundi theorem. And if S is a classical group, then its rank is bounded by a linear function of the order of pi. So applying this result, we consider case by case series of finite simple groups of Lie type, and they understand that for each free parameter series there are at most or at the order of pi cube choices to take the rank, the characteristic of the field, and the power L. And for two parameter series there are at most or at the power of pi square, and for one parameter series there are at most O of the order of pi choices. So in any case there are at most O of pi cube choices to find these free parameters, and no more find simple groups of this series from the property that its prime spectrum is contained in the our fixed finite set P of primes. And this proposition finishes our proof of the theorem, which gives a criteria of unrecognizability of finite group by its Gruenberg-Kegel graph, and then we apply this theorem and our results with Ilya Gorshkov obtained 3 years ago. We can conclude that we know the structure of any finite group which is almost recognizable by Gruenberg-Kegel graph. First of all, let us mention about our results with Ilya Gorshkov. If G is an almost simple group, then the following conditions are equivalent. Its Gruenberg-Kegel graph doesn't contain a indust freak-click. Its Gruenberg-Kegel graph is isomorphic to the Gruenberg-Kegel graph of some finite solvable group, and its Gruenberg-Kegel graph is equal to the Gruenberg-Kegel graph of some finite solvable group. And all groups, finite almost simple groups with these properties are known. So applying our theorem 1 and these results, we conclude that if G is a finite group which is almost recognizable by Gruenberg-Kegel graph, then G forced to be almost simple. Each group with this Gruenberg-Kegel graph as G is forced to be almost simple. 2 is non-adjacent to at least one odd prime in the Gruenberg-Kegel graph of G. And the Gruenberg-Kegel graph of G contains at least 3 pairwise non-adjacent vertices. And since we know that each recognizable by Gruenberg-Kegel graph forced to be almost simple, we have the following open problem. For any finite almost simple group, decide whenever is it recognizable by Gruenberg-Kegel graph, co-recognizable or unrecognizable. And if we solve this problem 1, then we can tell that we know all things about recognizability of a finite group by its Gruenberg-Kegel graph, and we can really tell that this direction of research is completely solved. So it's the base problem in this direction now. And let me mention some known results in this direction. First of all, 23 fine simple sporadic groups have the property that the question of recognition by Gruenberg-Kegel graphs for them is solved. These three groups are known to be so-called quasi-recognizable. So there are some partial solutions for these groups, and I hope that it will be ruled out in the near future. And there are remarkable results by Andrei Zavornitsyn in 2006. A series of exceptional groups of Lie type. It was the first infinite series of fine simple groups which was known to be recognizable by Gruenberg-Kegel graph, and two separate examples of recognizable and two recognizable groups. The groups PSL2Q are investigated by many other authors. The first paper was by Mina Hagi from Japan, and the paper, two papers by Free Khosravi. It's a very interesting authors. They are three brothers with same surname Khosravi, and with names Bahman, Bihman, and Benrose. Bikhosravi, and Bikhosravi. And there is a series of papers by these three authors. It seems very interesting. And Benrose Khosravi with Amir Khosravi, and Benrose Khosravi separately, groups with so-called PSL2Q, and groups, in particular groups PSL2Q, are investigated almost completely. There are distinct examples. Sometimes they are recognizable, sometimes then they are too recognizable, and sometimes they are unrecognizable. A very remarkable result that the group PSL16 over the field of order 2 is recognizable by its Gruenberg-Kegel graph. It's independent result by three brothers Khosravi, and independently by Andrei Zavornitsyn with distinct techniques, and very remarkable result since it was the first example of a fine group with connected Gruenberg-Kegel graph, which is recognizable by Gruenberg-Kegel graph. And in this slide, you can see a series of results by Iranian mathematicians about groups of Lie type of unbounded ranks, but over a very small field, which are known to be recognizable or too recognizable by Gruenberg-Kegel graphs. And let us continue. Small groups S with small prime spectrum, were ruled out in two papers by Anatoly Kondratyev and his PhD student in past Igor Khramtsov. And very remarkable result that the groups, very big, fine, simple exceptional groups of Lie type, these groups are of bounded ranks, but of very big order, usually of a very big order. These groups are known to be almost recognizable by Gruenberg-Kegel graph if the field of is Q equals to 1, 4, or 0 modulo 5. And there are two other examples of exceptional groups of Lie type which are recognizable by Gruenberg-Kegel graphs, and alternating graphs and alternating groups and symmetry groups were ruled out in papers by Iranian and Russian mathematicians. There are known results, then they are recognizable, they are unrecognizable. So here I provide just a very brief survey of this research area. There are some partial results for other series of fine groups. However, I don't think that there are really many results, and this problem, the solution of problem 1 is very far from complete. So let us continue another questions. Consider this our address book and assume that some person, for example, policeman, wants to describe all the persons living in this given flat, for example. And this policeman came to the door, knocked, and invited the person to come out and starts to enumerate 1 person, 2 persons, 3 persons, and so on. This policeman doesn't know is the number of persons in this flat finite or infinite. Can we help to this policeman to understand then this he or she can tell stop, the number of person in this flat is infinite and I don't need to continue. Really, we can't help. Let gamma be a simple graph whose vertices are labeled by pairwise distinct primes. Then we tell gamma to be a labeled graph and denote the set of labels by the P of gamma and call it the prime spectrum of gamma. And me and Peter have proved the following theorem. There exists a function, polynomial function of degree at most 7, such that for each labeled graph gamma, the following conditions are equivalent. There exist infinitely many groups H with such a graph, and there are at most f of v of gamma groups H with the same Gruenberg-Kegel graphs as gamma. There, v of gamma is the set of vertices of gamma. So we can present to this policeman a function, and then the policeman knocked to the door of a flat. This person can see to the graph drawn in the door and estimate the number of vertices and calculate this function. And if the number of persons who came out from the flat is more than this function on the vertices of drawn graph, then the policeman can tell, stop, you live with infinitely many neighbors and I don't need to try to count all of you. Let us prove this theorem. Take gamma to be a labeled graph, and let us assume that there are only finitely many groups with such that their Gruenberg-Kegel graphs coincide with gamma. From theorem 2, we know that each group G with this property forced to be almost simple. And if we take pi to be the prime spectrum of gamma, then it's a finite set of primes. And let us show that there is a polynomial function f such that when a number of almost simple groups G with the property that pi of G is contained in this our set pi of primes is at most f of the order of pi. Let us first of all apply our proposition 2. If pi is a finite set of primes, then the number of non-abelian simple groups S with the property that their prime spectra contained in pi is finite and is at most O of the order of pi cube. And then let us prove that for each finite simple group S with the property that its prime spectrum is contained in pi, the number of almost simple groups with circle S is at most O of the order of pi power 4. First of all, let us mention that there is a one-to-one correspondence between almost simple groups with circle S and subgroups of the group of auto-authomorphisms of S, which is a factor group of full authomorphism group of S by its inner authomorphism, which is isomorphic to S. And let us prove proposition that if pi is a finite set of primes and S is a simple group of Lie type, such that if the prime spectrum of S is contained in pi, then there is a polynomial function f such that the number of subgroups of auto-authomorphisms of S is bounded by this function, has upper bound in terms of this function, and this function f is at most O of the order of pi power 4. Why do we need to deal with groups of Lie type only? Really, for any sporadic group, there are at most two possibilities. sporadic group and the full orthomorphism group of this sporadic group, which usually coincides with this group, or have order twice of this fine simple group. For alternating groups, except of the case alternating group on 6 points, for almost simple group with alternating circle, there are only two possibilities: alternating group on endpoints and symmetry group on endpoints. So we can forget about sporadic or alternating groups. For alternating group on 6 points, there are at most uh, 5 possibility: alternating group, PGL 2, 9, M10, S4, and the full orthomorphism group of alternating group on 6 points. At most 5 choices. So let us finish this proof for groups of Lie type. We need to remind our magic lemma: if pi is a fine set of primes and S is a group of Lie type of rank n over the field of order q, which is a p power l, and if the prime spectrum of S is contained in pi, then the following statements hold. The number of choices for p is at most the order of pi, and the number of choices of this power l is at most the order of pi plus 1, and the number of pi-wise distinct divisors of l is at most the order of pi plus 1. This step is very important for our further proof. And if S is a classical group, then its rank is bounded by a linear function from the order of pi. And we need two group theoretical lemmas, but these are not very hard to prove, and you can try to do it like some exercise. If G is a group with a normal series of length R with cyclic factors, then this group can be generated by at most R elements. And if G is a group with a cyclic normal subgroup C, such that the factor group G by C is generated, then the number of supplements of C in G. What is a supplement? A supplement is a subgroup H such that G can be represented as a product of H and C. And the number of such supplements is at most the order of C power k plus 1. There, k is the number of generators of factor group G by C. It's not hard to prove. So let us prove proposition 3. Let us bound the number of almost simple group with simple circle of Lie type. And first of all, we know that the orthomorphism group of S has a very well-known structure. It's a semi-direct product of C to the direct product of groups G1 and G2. And C is either cyclic or having a very small order, at most 4. And it's cyclic only in the cases of PSL linear groups and unitary groups. And if it's cycle, then its order is bounded by this rank n. And otherwise, it has very small order. And G1 is cyclic, and its order is bounded by L. It's either L or 2L or either 3L. And G2 has order at most 2, except the case of the group of type D4, then it's S3. In any case, G2 is very small. So if we take n of G to be the set of all subgroups of a group G, then n of orthomorphism group of S is a union of subgroups H with such that HC by C equals to T, and T is a subgroup of G1 times G2. And let us look to these lemmas. We can try to estimate the number of groups of subgroups of G1 times G2. The number of subgroups G1 times G2 is bounded by a linear function of the order of pi. So the number of classes in this union is bounded by a linear function of pi. And now by lemma 2 about the number of generators. Each subgroup T from G1 times G2 is at most 2 generated or is at most 3 generated for the case D4. And then we apply this lemma about possible number of choices for Q, for N, for L, and so on. And then lemma 3 about the number of supplements to a normal subgroup, really to subgroup C here. And the number of subgroups H such that HC by C is T for each fixed T is at most 2 pi, order pi plus 3 cube. And in the case D4, we need to apply this lemma twice and possible receive some constant here. So it doesn't matter. Thus, the number of groups of subgroups of the orthomorphism groups of S is bounded by a polynomial function from the order of pi and is at most O of the order of pi power 4. And then here our bound is not strict, and the problem 2 is improve an upper bound for the number of almost simple groups with the same Gruenberg-Kegel graph, and in particular answer the question, is there a constant k such that for any almost simple group G there are at most k pairwise non-isomorphic finite almost simple groups with the same Gruenberg-Kegel graph, and what is the exact value of k? Note that for cases when group is simple and we need to bound it the number of simple groups with this Gruenberg-Kegel graph, there is a problem established by Andrei Vasilyev, Tukaurovka notebook, and there is a conjecture that this constant k for simple groups is at most 4. And this problem is active in investigating. If G is a sporadic group, then Mina Hagig described all the possibilities for groups with the same Gruenberg-Kegel graphs as sporadic groups. And after Maria Zvezdina has ruled out the case, then group G is alternating group. And to finish this investigation, it's necessary to consider the cases of coincidence of Gruenberg-Kegel graphs of two groups of Lie type, and then the characteristics of their field coincide. Mariana Zinovieva has ruled out this case, and for fields of distinct characteristics, she is investigating this problem, and this research is still in progress. And in the final part of my talk, let us consider the question of recognition of a finite group by isomorphism type of its Gruenberg-Kegel graph. A group G is recognizable by isomorphism type of its Gruenberg-Kegel graph if each group H such that the Gruenberg-Kegel graphs of G and H are isomorphic as abstract graph forced to be isomorphic to G. So the group G doesn't share its house with other groups. And by theorem 2, if G is recognizable by isomorphic time of its Gruenberg-Kegel graph, then it's forced to be recognizable by its Gruenberg-Kegel graph, and therefore by theorem 2 it's forced to be almost simple. So there is an open problem 3. Let G be an almost simple group. Decide whenever G is recognizable by isomorphism type of its Gruenberg-Kegel graph. There are several results in this direction. The first result was by Andrei Zavornitsyn in 2006. He has proved that the sporadic simple group Yanka the fourth is the unique finite group whose Gruenberg-Kegel graph has 6 connected components. So as a corollary, we conclude that the fourth group, finite simple sporadic group of Yanka, is recognizable by isomorphism type of its Gruenberg-Kegel graph. And recently, me and Peter in our joint paper have proved that two more groups, regroup over the field of order 27 and EH over the field of order 2 are recognizable by isomorphism types of Gruenberg-Kegel graphs. Let us discuss the proof for regroup and some moments for EH over the field of order 2. If G is a fine group such that its Gruenberg-Kegel graph is isomorphic as abstract graph to the regroup over the field of order 27, then it has isomorphism type of its Gruenberg-Kegel graph as follows. In particular, this graph is bipartite with parts of orders 5 and 1. And from our paper with Dush and Pagon 5 years ago, if G is a finite group such that its Gruenberg-Kegel graph is bipartite with parts of size 1 and 5, then the factor group of G by the largest normal solvable subgroup of order power of 2 equals to regroup of over the field of 27 elements. Therefore, Gruenberg-Kegel graphs of G and of regroup over the field of 27 elements coincide. And now let us take remarkable result by Andrei Zavornitsyn that all regroups are recognizable by Gruenberg-Kegel graph, and we conclude that G forced to be isomorphic to regroup over the field of 27 elements. And what about the group EH over the field of order 2? If G is a finite group such that gamma of G is isomorphic to the Gruenberg-Kegel graph of G is isomorphic to the Gruenberg-Kegel graph of EA2 as abstract graph, then first of all, the prime spectrum of G consists of 16 elements. We apply adjacency criteria for Gruenberg-Kegel graphs of fine simple groups and conclude that gamma of G has 4 connected components, and from these results we know the powers of all vertices of this graph. Since this graph is disconnected, the Gruenberg-Kegel theorem, Kristina Ilyenko in the next talk will tell about the Gruenberg-Kegel theorem in detail, so I miss this from this statement. Then the factor group of G by the largest nilpotent normal subgroup forced to be almost simple. And the number of connected components of the circle of this group is at least 4. We know the description of connected components of Gruenberg-Kegel graphs of fine simple groups, and taking the list of fine simple groups with at least 4 connected components of the Gruenberg-Kegel graphs. These results are by Williams and Kondratiev, and we take all the groups and using some reasonings without with powers of vertices and some group theoretical reasons rather complicate. We prove that the circle of G by F of G is forced to be equal to EA2. And in the final step, we prove that F of G equals to 1. It means that EH2 in particular recognizable by its Gruenberg-Kegel graph. And the proof of this fact is based on the fact that EH2 contains a subgroup of exceptional subgroup of Lie type D44 and the proof is based on results about element orders in covers of this subgroup. These results are by Andrei Zavornitsyn 8 years ago. So there is one more result in this direction. Recently, me and Mariana Zinovieva have proved that simple groups EHQ for Q 3, 4, 5, 7, 8, 9, and 17 are recognizable by isomorphism types of the Gruenberg-Kegel graphs. And here, since these results, we have two more open problems. Are there other simple groups which are recognizable by isomorphism types of Gruenberg-Kegel graphs? And are there almost simple but not simple groups which are recognizable by isomorphism types of the Gruenberg-Kegel graphs? And possible the answer to problem 5 is no, but I haven't checked still. And in the final moment of my talk, let me repeat link to our joint paper with Peter Cameron. You can find it in the archive. And then thank you for your attention.
Thank you, Natalia, very much for a very nice talk. It is, well, it is almost survey on some new and old result on the topic. Thank you very much.